Welcome to the Joy of Architecture. Today we're embarking on a really deep dive into database indexes. Now, you've likely used them, maybe you even know they generally make queries faster, but do you really get what's happening under the hood? The hidden mechanics, the delicate trade-offs, and why choosing the right index is less guesswork and, well, more engineering artistry.
That's exactly it. That's our mission today, really. We want to demystify these crucial data structures. We'll unpack how different indexes work internally, when they shine, when they, well, struggle a bit, and where you'll actually find them out in the wild. By the end of this deep dive, you should have a pretty rigorous technical understanding, enough to really guide your decisions as a software architect or maybe a database engineer. It's all about getting to the core of what makes your data fly, or unfortunately, sometimes crawl.
Okay, so let's unpack that a bit. At a high level, indexes are basically designed to make data retrieval way more efficient, right? They cut down on disk I/O, help avoid those painful full table scans.
Exactly. Think of them as these super organized structures. They store sorted key values, and each key has a pointer, basically, to where the actual data lives. But, and this is absolutely key, they always come with trade-offs.
Right, the trade-offs.
Yeah, they take up extra disk space, sometimes quite a lot, and there's maintenance overhead every time you change data inserts, updates, deletes.
So it's a balancing act.
It's the balancing act.
Yeah.
This trade-off is pretty central to, well, everything we're talking about today. Sure, the database query optimizer tries its best to pick the right path, but you, as the architect, often need to set the stage correctly for it.
Makes sense. So, where do we start? Let's kick things off with, I guess, the real workhorses, B trees, and their more common evolution, B+ trees. If you've ever touched a relational database, chances are you've been leaning on these pretty heavily.
Oh, absolutely. And the real brilliance of the B+ tree, which you see everywhere, like PostgreSQL, MySQL, and ODB, is its design. It's quite elegant.
Yeah.
See, unlike some older B trees, all the actual data, the real records, are stored only in the leaf nodes.
Okay, so what's in the internal nodes then?
They're purely navigational guides. Just keys and pointers pointing down to the next level. Think of it like a directory. This separation allows for a much higher branching factor.
Meaning the tree is wider and not as deep.
Exactly. So it's shallower, which means fewer disk reads, fewer I/O operations to find what you're looking for. And here's another neat trick. Those leaf nodes. They're linked sequentially, like a linked list.
Ah, so that must be great for range queries, like finding everything between date A and date B.
Precisely. It makes range queries super efficient. Now, how it works? Well, searching is kind of like a binary search within each node as you traverse down to a leaf. Inserting means finding the right leaf, adding the key. If that node gets too full, it splits, and those changes might bubble up the tree.
And deletions?
Similar process in reverse. Remove the key, and if a node gets too empty, it might merge with a sibling, again, possibly propagating changes upwards, rebalancing, and updates. Typically, an update to an indexed field is handled as a delete, followed by an insert.
So there's definitely cost to writes.
There is. That ongoing rebalancing, the index updates for modified data, that's what we call write amplification. There's an inherent maintenance overhead. But modern databases are pretty smart about it. PostgreSQL, for instance, has advanced stuff like Lehman and Yao for concurrency, HRT updates to sometimes avoid index updates entirely, even index deduplication now.
And index-only scans. I've heard of those.
Yeah, that's a big one. If all the columns your query needs are right there in the index itself, the database doesn't even need to go fetch the actual data row from the main table. Huge performance win, sometimes called a covered index.
Okay, so architecturally speaking, when do I absolutely reach for a B tree or B+ tree?
They're your go-to for point queries finding one specific thing, like a user by ID, unmatched. And as you guessed, they're excellent for range queries between, less than, greater than, thanks to those linked leaf nodes. Also fantastic for sorting results, order by, group by Y, enforcing uniqueness, like primary keys, and even prefix matching, like ABC%.
What about the kind of data in the column?
Good point. They work best on high cardinality fields, fields where there are lots of unique or distinct values.
Okay, so where do they not shine? What are the limitations?
Well, they're not your tool for full text search. You'd want something specialized, like a GIN index or a general inverted index for that. And for data with multiple values in one field, think arrays or JSON documents or columns with very few distinct values. That low cardinality stuff like status or gender.
Well, they're not usually the most efficient choice there. Bitmap indexes often win out.
Right. And where do we find them, mainly?
Pretty much every major relational database. PostgreSQL, MySQL, Oracle. MongoDB's Wired Tiger storage engine also uses them heavily. Their read performance, that O log n, is fantastic for high-throughput OLTP systems. Yes, writes have an impact, but modern optimizations make it manageable.
Okay, so B-tree versus, say, a hash index.
Choose B-tree if order matters. If you need ranges, sorting, or prefix matching, hash indexes are purely for exact equality checks.
And B-tree versus bitmap. B-trees for high cardinality, frequent updates. Bitmaps really shine for low cardinality, complex Boolean queries, especially in read-heavy analytical systems where updates are less frequent.
All right, let's switch gears. Hash indexes, you call B-trees workhorses. What are these?
These are the drag racers. Pure speed, but for a very specific track. They're built for one thing primarily: incredibly fast, exact match lookups.
How do they pull that off?
It's basically a hash table implemented on disk, or often in memory. It uses a hash function to map your key directly to a specific bucket or storage location. So when you search, you just hash the key, boom, go directly to that bucket. Then you might need a quick secondary search if multiple keys hash to the same spot. That's collision handling.
Okay, sounds simple enough. Insertion.
Similar process: hash the key, place it in the right bucket, handle any collisions. Updates usually mean rehashing, potentially moving the entry, so it's often like a delete then insert.
What's the catch?
Yeah.
They sound almost too good for exact matches.
The cache is maintenance, especially for disk-based hash indexes. Collision management is one thing, but the big one is revising. As your data grows, that underlying hash table needs to get bigger. Rehashing everything can be really expensive, causing a lot of random I/O, which disks hate.
Ah, okay. And concurrency.
That's another challenge. You need robust mechanisms like atomic operations or careful locking to handle concurrent access without messing things up.
So application-wise, where do these really excel?
Absolutely best for those exact match lookups, where use radix gives some value. Nothing beats them there, theoretically. They're also great for speeding up uniqueness enforcement during inserts. In-memory databases especially can leverage them for incredible performance because the random access pattern isn't as punishing as on disk. Amortize O1 lookup time is hard to beat.
The takeaway is pure speed for equals checks.
Pretty much. If you only need equality and speed is paramount, hash indexes are a strong contender, especially in memory.
But the limitations are significant, right?
Oh yeah. They are completely useless for range queries, sorting, order by Y, or prefix matching, like ABC%. The hashing process destroys any natural order in the data. And because of that random I/O during resizes and lookups, they're less common for general-purpose, disk-based indexing compared to B-trees. High numbers of duplicate values can also hurt performance.
Where might we see them?
PostgreSQL supports them for equality, TimescaleDB uses them, SQL Server has them for its memory-optimized tables, MongoDB uses hash-based sharding keys sometimes, so in OLTP they're great for specific targeted speed boosts on point lookups, but for OLAP analytics, generally unsuitable because they lack order.
Okay, interesting. Let's move on to something quite different. Bitmap indexes. These sound specialized.
They are very specialized, primarily for analytical workloads on a specific type of data. The core idea behind bitmap indexes is quite clever. They use bit vectors.
Bit vectors, like strings of ones and zeros.
Exactly. Imagine you have a column, like gender, with only male and female. You'd have one long bitmap for male and another for female. Each bitmap has one bit for every row in your table. If the 100th bit in the female bitmap is 1, it means the 100th row has the value female.
Ah, okay. And that's efficient for low cardinality data, columns with few distinct values.
Incredibly space efficient for low cardinality, yes. You only need one bitmap per distinct value. And their real power comes during querying. They can perform bitwise logical operations A and D or R, not directly on these bitmaps, extremely fast.
So if I have a query like find all active female users in the East region.
Perfect example. The database would grab the bitmaps for female active and East, perform bitwise AND operations on them, and the resulting bitmap tells you exactly which rows match all conditions. Then it just converts those 1 bits back into row IDs.
That sounds really fast for complex queries. What's the downside? Must be writes again.
Bingo. Updates are the Achilles heel of bitmap indexes. Changing a single row's value can be quite costly. You might have to decompress the bitmap, find the right bit, flip it, re-encode it. Worse, this can create hotspots for concurrency. Since many rows share the same few bitmaps for low cardinality, lots of updates trying to modify the same bitmap can cause serious contention.
Okay, so definitely not for high update environments.
Absolutely not. Nightmare fuel for write-intensive OLTP.
So the sweet spot is,
Low cardinality columns, gender, status, country codes, that sort of thing, and read-intensive OLTP or data warehousing scenarios. They are absolute superstars for complex multi-attribute queries that involve lots of ANDs and ORs. Aggregations can also be very fast.
the definite no-go zones.
High cardinality columns like unique IDs or email addresses, the space savings disappear and the overhead skyrockets. And as we said, any kind of write-intensive OLTP system, the update overhead and concurrency contention are just too problematic.
So the takeaway, analytical superpower, OLTP nightmare.
Couldn't have said it better myself. You find them heavily used in Oracle for data warehousing, systems like StarRocks. PostgreSQL has BRIN indexes, which are conceptually related block range indexes, serving a similar data skipping purpose based on summaries, but not quite the same bit-level structure. Their home turf is OLTP. You generally avoid them in OLTP.
All right, moving on to something that sounds flexible. GEAST, generalized search tree.
Yeah, GSIS is really interesting because it's less of a specific index type and more of an extensible framework. Think of it as a toolkit for building indexes on complex data types that just don't fit neatly into a simple linear order like B trees require.
Complex data types like what?
Geometric shapes, geographical data, time ranges, even things like full-text search documents. Data where a simple less than greater than comparison doesn't make sense or isn't sufficient. Internally, it's a height-balanced tree. Kind of like a B tree, but with a key difference. Its subtrees can overlap.
Overlap. How does that work?
It's essential for multi-dimensional or complex data. Imagine indexing geographical regions. One region might partially overlap another. A standard B tree can't really handle that structure efficiently, just allows it. The generalized part means that you, the developer or extension author, provide specific methods functions, really, that tell GIST how to handle your custom data.
So GIST provides the tree structure, and I provide the logic for my specific data.
Exactly. You provide methods like consistent for searching, does this query match this subtree? Penalty for insertion, which child node is the best fit? Union to combine information, and others for splitting and adjusting nodes. GIST handles the tree mechanics, your code handles the beta-specific logic.
That sounds powerful, but potentially complex. What about performance and maintenance?
Searching might involve exploring multiple paths down the tree because of that potential overlap, so it might not be quite as direct as a B-tree search. Insertion and updates involve running your custom logic, like the penalty function, and recalculating parent node information, which can definitely be more expensive than standard B-tree maintenance. Some GIST implementations can also be lossy, meaning they might return a slightly larger set of candidates that need a final check against the actual data. Saves index space or complexity, but adds a recheck step.
So the prime use cases are these complex, nonlinear data types.
Absolutely. Geometric data, spatial data, like in PostGIS, range types in PostgreSQL, full text search. When you have specialized operators like, does this polygon overlap that one, or is this time range contained within another? If you need to build a completely custom index for a user-defined type, GST is the framework that enables that.
The takeaway then, flexibility for complexity. Your go-to when B-trees just won't cut it for the data shape or query type.
Precisely. It's a core feature in PostgreSQL, and PostGIS relies heavily on it to implement R-tree functionality for spatial data. But for simple scalar data, stick with B-trees. They're much more efficient for that.
Okay, sticking with PostgreSQL for a moment, let's talk about GAN. Generalized Inverted Index. This one comes up a lot with arrays and JSONB, right?
Yeah, GIN is another powerful PostgreSQL index type, specifically designed for indexing composite or multi-value types. Think arrays, JSON and B documents, or full-text search vectors. Its core structure is an inverted index.
Inverted? How so?
Instead of the usual index mapping a row ID to its values, an inverted index maps each unique value or token within those composite types to a list of all the row IDs that contain that value.
So one row might be listed under multiple values.
Exactly. If a row has an array 1, 5, 10, that row's ID will appear in the posting lists for 1, 5, and 10. The generalized part comes from its use of operator classes. These define how to extract the individual items to be indexed from the composite type, like extracting words from text, elements from an array, or keys and values from JSONB.
How did that affect searching and writing?
Searching becomes incredibly fast for certain query types. If you want to know which rows contain the value 5, the index just retrieves the posting list for 5. If you ask which rows contain 5 and E10, it gets the lists for both and finds the intersection using very fast bitmap operations. This is why GIN only supports bitmap index scans internally. Writing, however, is generally slower than B-trees.
Why is that? Right amplification again?
Precisely. If you insert or update a row with an array of 100 elements, you might need to update 100 different posting lists in the GIN index. That's significant write amplification. PostgreSQL has an optimization called fast update. It buffers newly indexed items in a temporary in-memory list before merging them into the main GIN structure in batches. This helps smooth out write performance, but the batch updates, when they happen, can still cause temporary performance spikes.
Okay, so the sweet spot for GIN is searching within these composite types.
Absolutely. It's the go-to for full text search in Postgres. Excellent for array containment queries. Does this array contain value X? Super powerful for querying JSON-B documents. Find documents where the tags key contains urgent. Essentially, if you have multi-value data and your queries are about the presence or containment of specific items within that data, GIN is likely your best bet.
The takeaway: unlocks efficient search on arrays, JSON-B, and text.
Yep. But it's not for range queries. It doesn't preserve order. And for simple scalar values, B-trees are still better. And watch out for that write overhead on very high throughput write workloads.
And it's mainly a PostgreSQL thing.
It's a native, highly optimized index type in PostgreSQL. Systems like ubiquitous, which reuse parts of Postgres, also support it, though their internal implementation might differ slightly due to their underlying storage. It's highly effective in OLTP for analyzing semi-structured data.
Right, let's step into the spatial realm with R trees. You mentioned PostGIS uses Jest to implement these.
That's right. While GIS provides the framework, the R-tree logic is what makes spatial indexing work efficiently. R-trees are specifically designed for multidimensional data. Think points, lines, polygons on a map.
So how do they differ from B trees internally?
Like B-trees, they're typically height-balanced trees aimed at disk-based storage. But instead of simple linear keys, they group nearby spatial objects using their minimum bounding rectangles, or MBRs. An internal node in an R-tree stores MBRs that enclose all the objects in their child nodes. Leaf nodes store the MBRs of individual objects along with pointers to the actual object data. A key characteristic, similar to GIS, is that the MBRs of sibling nodes can overlap.
Okay, that overlap seems common for complex data. How does searching work?
It generally follows a filter and refine approach. You start at the root and check which child MBRs overlap with your query region. You recursively descend down all overlapping paths. That's the filter phase. Once you reach leaf nodes, you perform exact geometry checks on the actual objects within the overlapping leaf MBRs. That's the refine phase.
Sounds effective, but what about maintenance? That overlapping structure sounds complex to update.
It is. R-tree maintenance, especially with frequent inserts, deletes, or updates, which are often delete plus insert, can be costly. When you insert an object, you need to find the best leaf, potentially split nodes if they overflow, and then propagate MBR adjustments back up the tree. Deleting can cause nodes to become underfull, requiring merges and potentially reinserting orphan entries. These structural changes can cascade. Concurrency is also traditionally challenging. Modifying the tree structure might require locking large portions of the tree, potentially even up to the root, which limits concurrent operations. Modern variants like R-trees or R-linked trees have strategies to improve concurrency with more fine-grained locking.
Bulk loading sounds preferable then.
Definitely. For static or infrequently changing spatial datasets, bulk loading an R-tree is much more efficient than inserting objects one by one.
So architecturally, when do I choose R trees?
They are the primary choice when your core task involves managing and querying spatial data. Geographic Information Systems, GIS, computer-aided design, SAD, location-based services. If your queries involve spatial predicates like find all points within this polygon, which roads intersect this area, or find the nearest neighbors to this point, R-trees are specifically designed for that.
The takeaway: the specialist for spatial queries.
Exactly. But they're generally poor for frequent updates, making them less ideal for highly dynamic OLTP systems focused purely on spatial changes. And obviously, they're not meant for standard one-dimensional data or non-spatial key lookups.
And we find them in PostGIS via GC elsewhere.
Yes, dedicated spatial databases. Some embedded databases like DuckDB and RayMaDB also support R-tree variants. They shine in OLTP for analyzing large spatial datasets. In OLTP, you might use them, but you need to be mindful of the update costs.
Okay, let's switch dimensions again, this time to strings. Trie-based indexes or prefix trees. What's the story here?
Tries are fascinating. They excel specifically at handling string data, especially prefix-based operations. Their internal structure is a tree, but not based on comparing whole keys like a B tree. Instead, each node typically represents a single character. The path from the root node down to any other node defines a string or a prefix.
So CAT would be a path.
Exactly. And if you also had CAR, they would share the C and A nodes. This sharing of common prefixes is what can make tries potentially very space efficient for certain datasets. Searching is intuitive. You just traverse the tree character by character based on your search string. Insertion involves adding new nodes along the path if they don't exist, and marking the final node as representing a complete key.
Sounds neat. What are the challenges or overheads?
Space can actually be a major issue. A naive try implementation might have pointers at each node for every possible character in the alphabet. For example, 26 for English letters or 256 for bytes. If your keys don't densely cover all character combinations, you end up with very sparse nodes and a lot of wasted pointer space.
So compaction is important.
Absolutely critical. Techniques like Patricia tries or radix tries, or more modern variants like ART, adaptive radix tree, or HRT, height optimized try, are designed specifically to compress the try structure and reduce that space overhead, sometimes dramatically, like 70% or more. Concurrency can also be tricky with traditional locking on nodes, but advanced implementations like concurrent hash tries, SU tries, use clever techniques like compare and swap, CAS, to offer lock-free, highly scalable concurrent operations.
Okay, so where do tries really shine? What are the best use cases?
They are unbeatable for prefix matching. Think auto-completion features in search bars, also great for dictionary lookup, spell checkers. Network routing tables often use specialized tries, like Patricia tries, for efficient longest prefix matching to determine where to send network packets. They can also be used for certain multi-attribute searches.
So the takeaway, the master of prefixes and string lookups.
That's a good way to put it. If your workload is dominated by string operations, especially prefix searches or exact string matching, tries, particularly optimized variants, are a very strong candidate.
And where do they struggle?
They're generally not great for range scans on the entire dataset, as traversing the tree character by character can lead to poor cache locality compared to the block-oriented access of B trees. Searching for arbitrary substrings, not just prefixes, usually requires different techniques. And as mentioned, scalability without good compaction and concurrency control can be an issue for very large datasets.
Where do we see tries in the real world?
You find them in embedded systems like ExtremeDB. Their principles are relevant to key ordering and partitioning in some distributed systems like Cassandra or DynamoDB. Optimized versions like ART and HotT are foundational for many high-performance in-memory key value stores. They're less common as a general-purpose disk-based index in traditional relational databases compared to B-trees, but they excel in their niche.
Okay, let's talk about something many people interact with daily without realizing it, the inverted index. You mentioned GIN uses this principle, but this is the broader concept, right? The core of search engines.
Absolutely. The inverted index is the fundamental data structure powering most large-scale, full-text search engines like Google Search, Elasticsearch, Solr, etc. We touched on the idea with GIN. It inverts the relationship. Instead of mapping documents to their content, it maps content specifically, terms or words, back to the locations, documents, or even positions within documents where they appear.
So it's like the index at the back of a book, but for potentially billions of documents.
That's a perfect analogy. It typically has two main components. One, the vocabulary or dictionary, a list of all unique terms found in the entire document collection, usually sorted. Two, posting lists. For each term in the vocabulary, there's a list of identifiers pointing to where that term occurs. This list might just contain document IDs, or for more advanced searching, like phrase queries, it might also include the positions of the term within each document.
How is it built and searched?
Building it involves parsing documents, breaking them into tokens, words essentially, normalizing them, like lowercasing, stemming, building the vocabulary, and generating those posting lists. Searching involves pre-processing the user's query, similar parsing normalization, looking up each query term in the vocabulary to get its posting list, and then efficiently combining these lists using set operations intersection for any queries, union for OR queries. Finally, results are typically ranked based on relevance, using algorithms like TF-IDF or BM25.
It sounds computationally intensive to build and maintain, especially with constant updates.
It is. That's the main maintenance challenge. Frequent updates, deletes, or inserts are costly because they involve parsing, tokenizing, and modifying potentially many posting lists. Most modern search engines handle this using a segmented approach. New documents or updates go into smaller, new, immutable index segments. These segments are searched along with the older, larger segments. Periodically, a background process merges these smaller segments into larger ones, efficiently handling dilutions, often marked with tombstones initially, and optimizing the structure. This provides near real-time search capabilities. Storage overhead can also be significant, but compression techniques for both the vocabulary and posting lists are crucial and
Yeah.
heavily used.
So the prime use case is obvious. Full text search.
Undeniably, full-text search engines, document retrieval systems, log analysis platforms, anywhere you need to find documents based on their content, using Boolean logic and/or not, or proximity queries, find database near index.
Takeaway. The engine behind content search.
Precisely. But they're not designed for retrieving data based on strict ordering, like finding the 10 most recent orders that usually requires sorting after retrieval or a different index type. And while near real-time updates work well, the background merging means they might not be suitable for systems demanding extremely low, guaranteed latency on every single write operation. For simple structured data lookups, B trees are far more efficient.
And we see them in Lucene, powering Elasticsearch, Solr, specialized search databases.
Right, and search features within other databases often rely on inverted index principles, like PostgreSQL's GIN. They are inherently designed for distributed systems and are the workhorse for OLTP tasks involving text analytics. Hashtag modern and emerging indexing paradigms.
Okay, let's shift towards some more modern or specialized paradigms. What about zone maps or min-x indexes? These sound simpler.
They are. Zone maps are wonderfully simple yet effective, especially in analytical systems. They don't index individual rows. Instead, they store lightweight summary statistics, typically just the minimum and maximum value for large zones or regions of data on disk, often corresponding to storage blocks or groups of blocks.
So just the min-max for a whole chunk of data. How does that help?
It enables very efficient data pruning or data skipping. Imagine you have data sorted by date, and a zone map tells you that a particular 10,000-row block only contains dates from January 2023. If your query asks for data from March 2024, the database can look at the zone map for that block and instantly know none of the data it needs is in there, so it doesn't even need to read that block from disk.
Skips reading entire blocks. That could save a lot of I/O.
A huge amount, especially in analytical queries scanning large portions of a table. It's a metadata layer that helps avoid work. Maintenance overhead is typically very low. These are often generated automatically by the database system, perhaps during data loading or in the background. They're much, much smaller than traditional row-level indexes.
Is there a catch?
The main thing is they don't offer row-level precision. They can tell you a block might contain data matching your query, but not which rows. You still need to scan the relevant blocks. Also, they can become stale within a transaction. If you insert data, the zone map might not reflect that immediately, but this eventual consistency is usually fine for analytical workloads. They work best when data has some natural clustering or order, like that date example. If data is completely random, the min-max range for each block will likely be very wide, and you won't get much pruning benefit.
So best use cases.
They are a fantastic complement to columnar storage systems, ideal for OLTP and data warehousing workloads, especially those involving range queries on large tables. Great for clustered or ordered data. Medium to high selectivity queries benefit most.
Takeaway. Lightweight I/O reduction for analytics.
Exactly. Don't use them for OLTP. They're not designed for precise lookups or transactional consistency, and they're less effective on randomly distributed data.
Where are these used?
Very common in modern analytical databases. DuckDB uses them expensively and automatically. Oracle has similar concepts like storage indexes and Exadata. Columnar databases like MongoDB and cloud data warehouses Redshift, Snowflake, BigQuery, Databricks all rely heavily on this type of metadata for pruning.
All right, next up, LSM trees. Log-structured merge trees. These have become incredibly popular, especially in the NoSQL world. Why is that?
LSM trees represent a fundamental design choice to optimize for write performance, often at the expense of some read complexity. That makes them incredibly well-suited for write-intensive workloads. The core idea is to transform random write operations, which are slow on traditional spinning disks and even have overhead on SSDs, into sequential writes.
How do they achieve that transformation?
It's a hierarchical structure. All incoming writes, inserts, updates, even deletes, which are often marked with a special tombstone record, first go into an in-memory data structure, typically sorted, called the mem table. Simultaneously, the write is appended to a write-ahead log, WAL, on disk for durability in case of a crash.
Okay, so writes hit memory first, which is fast.
Hmm.
What happens when memory fills up?
When the mem table reaches a certain size, its entire sorted contents are flushed to disk as a new, immutable file called an ssstable sorted string table. This flush is a largely sequential write operation. These ssstables are then organized into multiple levels or tiers on disk, level 0, level 1, etc.
Immutable, so you never modify an SS table once it's written.
Correct. Updates or deletes for existing keys simply write a new entry with a newer timestamp or version to the mem table, which eventually gets flushed to a new SS table. Older versions and older SS tables become obsolete. This leads to the crucial background process in LSM trees, compaction.
Compaction, what does that involve?
Compaction processes run continuously in the background. They read SS tables from one or more levels, merge their sorted contents, discard the obsolete or deleted entries, the tombstones, and write out new consolidated SS tables to a higher level. This process is vital. It reclaims disk space, removes deleted data, and importantly, reorganizes the data to make reads more efficient. But compaction itself consumes I/O and CPU resources.
So reads have to potentially check multiple places.
Exactly. A read operation first checks the mem table. If the key isn't there, it has to check the SS tables, typically starting from the newest, level 0, and working its way down through the levels until it finds the key, or determines it doesn't exist. To speed this up, LSM trees heavily rely on Bloom filters. These are probabilistic data structures stored alongside SS tables that can quickly tell you if a key definitely does not exist in that file, allowing the read to skip searching it entirely.
Okay, so there are inherent trade-offs here.
Big time. We talk about 1. Write amplification. Data gets written multiple times, once to the wall, once to the mem table in memory, then flushed to an S table, and then potentially rewritten multiple times during compactions. 2. Read amplification. A single point read might need to check the mem table and multiple SS tables across different levels. Range scans need to merge data from multiple SS tables. 3. Space amplification. Old versions of data and tombstone markers can accumulate on disk until compaction cleans them up, meaning the disk usage can be significantly higher than the logical size of the data. Tuning the compaction strategy is absolutely critical to balancing these factors and avoiding performance jitter.
So given these trade-offs, when are LSM trees the right choice?
Their sweet spot is definitely write-intensive workloads. High rates of inserts, updates, deletes, think key value stores, time series databases, message queues, anywhere data is constantly flowing in. They are particularly effective on SSDs, where sequential writes are much faster than random writes.
Takeaway. Write optimized, but with read space compaction complexities.
Precisely. They might not be the best choice for predominantly read-heavy workloads where the absolute lowest read latency is paramount, or for very small data sets where the overhead isn't justified.
And they're everywhere now, right?
Oh, yeah. Foundational to many widely used systems. LevelDB, RocksDB, which is used by many other databases, HBase, Apache Cassandra, TidyB, ScyllaDB, MongoDB's Wired Tiger storage engine option. Even systems like Google Spanner use LSM-like structures. They're huge in the OLTP world for NoSQL and distributed databases because of that write throughput and built-in MVCC multi-version currency control from the immutable SS stables, allowing non-blocking reads. They're also being adapted more for analytical, OLTP, or hybrid HTTP workloads.
Okay, let's dive into something very current. Vector indexes, or ANN indexes. This feels very tied to the AI boom.
It absolutely is. Vector-ANN indexes are designed to solve a specific problem that's become critical in the AI era: finding similar items in massive high-dimensional vector spaces. Traditional indexes are great for exact matches or ordered ranges on simple data types, but how do you efficiently find images similar to a given image or text passages with similar semantic meaning? That's where vectors come in. AI models often represent complex data like images, text, or audio as numerical vectors in hundreds or thousands of dimensions.
And finding the nearest neighbors in that high-dimensional space is computationally hard.
Extremely hard for exact nearest neighbors, KNN search. The curse of dimensionality makes traditional spatial indexes like R trees break down. So ANN, approximate nearest neighbor indexes, make a crucial trade-off. They sacrifice guaranteed 100% accuracy for dramatic speed improvements. They aim to find most of the truly newest neighbors very, very quickly.
Okay, trading accuracy for speed. How do they work internally? What are some common types?
There are several approaches. Some popular ones include HNSW, Hierarchical Navigable Small World. This builds a multi-layered graph structure. Searching involves greedily navigating through layers, starting sparse and getting denser, to efficiently zoom in on the likely nearest neighbors. It's known for good performance and supports dynamic insertions well. Annoy, approximate nearest neighbors.
Okay.
Uses random projection trees, builds multiple trees and searches across them. It's often very memory efficient and can be mapped directly from disk, but the index is typically static, hard to update without rebuilding. Facey AI, Facebook AI Similarity Search. This isn't one algorithm, but a library from Meta AI offering many different index types, often combining techniques like inverted file structures, IVF for partitioning the space, and product quantization, PQ, for compressing vectors. It's highly optimized, supports GPU acceleration, and offers various accuracy speed trade-offs.
Dynamic updates sound like a challenge for some of these.
Yes. HNSW is generally considered good for dynamic insertions, but handling deletions efficiently, repairing the graph links, avoiding fragmentation is still complex. Annoy, being static, is poor for dynamic data. Face supports dynamic operations, but they can be computationally expensive depending on the specific index type used. Memory consumption is also a big factor. HNSW graphs can consume significant RAM. Annoy is often more memory frugal. Face resource usage varies greatly with the chosen index and whether GPUs are involved.
So the use cases are all about similarity.
Exactly. Similarity search is the killer app. Finding similar images, audio clips, product recommendations, users who like this also liked. Finding semantically similar text documents for search or question answering. A huge modern use case is retrieval augmented generation for large language models, LLMs. You convert your documents to vectors, index them, and when a user asks a question, you find the most relevant document vectors using ANN search and feed that context to the LLM to generate a better answer.
Takeaway: the search engine for high-dimensional meaning and similarity in the AI age.
Perfect summary. But remember, they provide approximate results. If you absolutely need the guaranteed exact K nearest neighbors, ANN might not be suitable. And they're obviously not for standard scalar data lookups.
Where do we find these? Are they separate databases?
Both. There are libraries like fakeass, Annoy, HNSWlib that you can integrate into your applications. There are also dedicated, purpose-built vector databases like Milvus, Pinecone, Weaviate, Chroma, Qdrant, Zillus Cloud, designed from the ground up for storing, indexing, and querying massive vector datasets. And increasingly, traditional databases like PostgreSQL with pgvector, Oracle, Elasticsearch are adding vector storage and ANN indexing capabilities directly. They're becoming crucial infrastructure for both analytical tasks on unstructured data and real-time OLTP features like recommendations or fraud detection based on similarity.
Finally, let's touch on something really cutting edge: learned indexes. Using machine learning as the index. That sounds wild.
It is a fascinating and potentially revolutionary idea. Instead of using traditional data structures like B-trees with explicit pointers to navigate data, learned indexes employ machine learning models to predict the position or rank of a key within a sorted dataset. The core assumption is that the distribution of your data, its cumulative distribution function, or CDF, can be learned and approximated by an ML model, like a neural network or a spline.
So instead of following pointers, you ask a model, where should key X be?
Essentially, yes. You feed the key to the model, it outputs a predicted position, e.g. it should be around the 8,750th record. Because the model is just an approximation, this prediction might be slightly off. So you then perform a small, localized search, like binary search or even linear scan, around that predicted position in the actual sorted data array to find the exact key or determine its insertion point. The promise is potentially much smaller index sizes. The model might be more compact than complex pointer structures and faster lookups. Model inference, especially in modern hardware or in memory, can be faster than traversing a deep tree.
That sounds amazing. What are the catches? I sense big catches.
Yeah, there are definitely challenges. The biggest one is handling updates, inserts, and deletes. When you insert or delete data, you change the underlying data distribution that the model learned. This can cause the model's predictions to become less accurate over time.
So you have to retrain the model.
That's the most significant maintenance overhead. Retraining can be computationally expensive and time-consuming, especially if the model is complex or the dataset is large and disk-resident. How often you retrain and how you handle updates between retraining becomes a critical design problem. Researchers have proposed various strategies, leaving gaps for in-place insertions, using small delta buffers to temporarily store changes, or more complex structures like the bucket-based learned index, BLI, which keeps data globally sorted but allows local unsortedness within buckets. Concurrency also needs careful design, often involving granular buffers or lock-free approaches. Bulk loading can also be slower initially than traditional methods because you need to train the model.
Okay, so writes are definitely the pain point. Where might these actually work well?
They show the most promise in read-heavy or read-mostly scenarios, particularly on data where the distribution is relatively smooth and predictable, easier for an ML model to learn accurately. Research has shown significant performance gains, especially for in-memory databases where the cost of model inference is very low compared to pointer chasing that might cause cache misses. They also tend to work better for numerical keys than complex string keys, which are harder to model effectively. They offer less advantage for general range queries compared to point lookups.
Takeaway. AI predicting data location potentially smaller faster for reads, but write retraining complexity is high.
That's a good summary. It's still an active area of research, but we are starting to see concepts appear in commercial systems, often as part of broader autonomous or AI-driven database features. Oracle Autonomous Database, Azure SQL Database mention AI-driven indexing strategies. SAP has evaluated related research like ALX Plus for OLTP.
So more likely to be an internal optimization chosen by the database itself, rather than something an architect explicitly creates today.
For the most part, yes, especially the fully autonomous retraining aspects, but understanding the principles is valuable as these techniques become more integrated. Hashtag tag tag outro.
Wow, okay, so we've really covered a lot of ground there. It's clear the database indexes are definitely not a one-size-fits-all kind of deal.
Right.
We went from the absolute basics, the foundational B trees powering most relational systems, to specialized things like R trees for spatial data.
The super fast hash indexes for those exact matches, the analytical powerhouses like bitmap and inverted indexes.
Right, and then into the more modern paradigms. LSM trees totally changing the game for write-heavy loads, vector indexes becoming absolutely critical for AI and similarity search.
And even peering into the future with learned indexes using ML. Each one has this unique internal dance, right? Different data structures, different algorithms. Each has its sweet spot for performance, but also those unavoidable trade-offs, reads versus writes, memory versus disk, concurrency challenges.
And understanding those nuances, those trade-offs, that's really what separates someone just using a database from someone who can truly architect a high-performance system around it.
Couldn't agree more. It's about making informed choices based on your specific data and workload patterns.
So here's a thought to leave everyone with, maybe a bit provocative. We see data exploding volume, variety, velocity, high-dimensional vectors, real-time sensor streams, complex graphs, and AI is constantly reshaping how we even think about accessing information. What's next? What kind of completely new indexing paradigms might emerge in the coming years that could make even some of what we discussed today seem, well, quaint? What new data shapes will demand entirely new ways of indexing?
That's the exciting part, isn't it? The field is constantly evolving.
Absolutely. Well, this deep dive was just fascinating and hopefully give you a much clearer picture of the indexing landscape. It's just one piece, of course, in building robust performance systems. If you found this discussion valuable, be sure to subscribe to Joy of Architecture. We'll keep exploring these fundamental building blocks that make our digital world tick